Wow, this is another lovely and wonderful day. Welcome to Physics Meal. Today on Physics Meal, we are going to look at motion part 5. Part 5 of motion. And in motion part 5, we are looking at graphical solution to accelerated motion. You remember that in our last video, we looked at how we can use equations to solve problems on accelerated motion. We saw the 4 main equations that we can use in solving those problems. So today we want to look at how we can use graph in solving equations on accelerated motion. Subscribe to our YouTube channel and make sure that you follow us on Facebook. It's very important. Our Facebook page is Mathematics and Science Mail, or you can still follow Engineer Ike Okechukwu on Facebook. Okay. Alright, so let's begin. Now in motion we have so many graphs that we encounter. We have the distance time graph. The distance time graph. So the distance time graph is the graph of distance versus what time, distance against time when you draw this graph. So we have distance against time, although we normally use x to represent distance in meter, time in seconds. Distance time graph. Okay, now distance time graph is one of the graphs we have in motion. But it's important that we know that distance time graph, the major thing we consider in distance time graph is usually the slope. The slope of a distance time graph is what? Is speed. So if you have a distance time graph in this one, the slope of a distance time graph is what? Is speed. We have another graph that is common, that's the displacement time graph. Displacement time graph. Displacement time graph. That is when you draw the graph of displacement. We still use x to represent displacement. Time is still t in seconds. So if you draw the graph of displacement against time, the slope of that graph, when you take slope, the slope of a displacement time graph is what? Velocity. So distance time graph, displacement time graph, they are part of the graphs that you actually encounter in your study of what? Of motion. You will usually see these graphs in the study of motion. But as far as accelerated motion is concerned, our business is on velocity time graph. Velocity time graph. So that's the graph of interest. So we are looking at velocity time graph. Velocity time graph. That's the graph. This is the graph. In some cases, they also call it speed time graph. Okay, so this is the graph of velocity against time. The graph of velocity against time. It is also known as speed time graph. It's also known as speed time graph. You know why we are just using speed and velocity together. We explained that when we started motion. We said that we'll be using speed and velocity to mean the same in our calculation, because most of the things we'll be calculating, they are in terms of the magnitude. Remember that velocity is a vector quantity, speed is what? A scalar quantity. So two of them are not necessarily, they are not the same, but in terms of magnitude they are the same. The difference is that velocity has what? Direction. So we say in our calculations we'll be using speed and velocity to mean the same thing, since we are concentrating on the magnitude, that size only. Alright, we explained that previously. Okay, now we have different regions in a velocity time graph. That's the first thing we must understand. We have different regions in a velocity time graph, and we'll be explaining those regions so that you understand what the regions are. So we have different regions in a velocity time graph. Well, we'll have different regions in a velocity time graph. We have different regions. The generalized graph below will be used to explain these regions. So let's put up a generalized graph, a generalized velocity time graph. Okay. Velocity is in meter per second. Now anytime you are placing graph, you label your axis properly with their unit indicated, and time, let me say time is in seconds. Okay, let me put the generalized graph in this form. Okay, I can, for explanation's sake, I can have this. Let me dot this. Okay, let me still draw this one. Okay, let's say T now, and here E. And here is our E. Okay, let's describe the region. This is a motion. Let's describe these regions. Let's explain them. So, the first region, 1, the region that slopes upwards. That is the region that moves like this, that slopes upwards, is the region of acceleration. So in every velocity time graph, anytime you see a region like this that slopes upwards, that area or that region is talking about what? Acceleration. That particular region, that particular place. These 2 points, this indicating acceleration. So everything that happens here is everything about what? Acceleration. So the region that slopes upwards is what? Acceleration. So in this case, OA is the region of acceleration. So this OA indicates when the body is accelerating. Therefore, OA, that's the line OA, this line indicates this line OA. But let me write line OA indicates when the body is undergoing acceleration. So this body is undergoing acceleration here. Very important. Okay? Number 2. The region that is horizontal. Our horizontal region. The region like this. Talking about AB here now. Is the region of uniform velocity or speed. Is the region of uniform velocity or speed. At this point, at this region, velocity is constant. That means velocity is not changing. Thus, acceleration is 0. So at this region, we don't have acceleration. Acceleration becomes 0 because velocity is not changing. Velocity is constant. And we know that during uniform velocity, acceleration becomes what? Becomes 0 for accelerated motion. So acceleration is 0. So in this case, AB, line AB is region or shows uniform velocity. Shows uniform velocity. Line AB shows uniform velocity. Okay. Then the third region now. The region that slopes upwards, downwards, sorry, that slopes downwards. Does this now is or represents deceleration or retardation. So this region now, DE, line BE, shows deceleration or retardation. That's line BE, shows deceleration or retardation. That's what it shows. So here is deceleration or retardation. So irrespective of how they draw a velocity time graph, you can actually interpret it. Since you now know what these lines represent, from here to here what it represents, from here to here what it represents, from here to here what it represents. So when you know what all these represent, you can actually interpret a velocity time graph, no matter how the nature of the graph, no matter the nature of the graph. You now know when we have acceleration, when we have deceleration, when we have uniform what? Velocity or speed. So if I have, let's say I have this. Let's say I have this now. I have a graph like this. Time in seconds, velocity meter per second, and I have this, I have this, I have this, I have this. If someone said, what happened in this motion? In this motion, a body accelerated, reaching a particular velocity. You see it accelerated, got to this velocity. Then from that velocity, it did not move, it decelerated to a new velocity, which you can trace to this point, and then move with uniform what? Velocity before deceleration. You see, that's what happened. Accelerated, decelerated, move with uniform velocity, then decelerate. So it means if I now have something like this, that and that, it means the body just accelerated and then decelerated. Okay? See, it's in different forms. No matter the form of the velocity time graph, you'll be able to explain it. So if I have this now, this body did not accelerate, there is no region of acceleration. So this body started with an initial velocity and moved uniformly before decelerating to what? Decelerating to rest. Now, we know that if the body moves from here, it starts from rest. It starts from rest. So this body accelerated from rest. That's from the origin now, from rest. Move with uniform velocity, then decelerated. But if I now have this body did not accelerate from what? Rest. So you cannot expect the initial velocity to be what? To be zero. So you accelerated from a particular velocity here, and then attained a new velocity, maybe move with uniform velocity before coming to rest, undergoing deceleration. So I believe that it is clear to you now what each of the lines in a velocity time graph represents. And once you now know what they represent, you can now be able to carry out calculations, or you can be able to analyze a velocity time graph. All right, in our next video, we are going to see the uses of a velocity time graph. We're going to see the uses of a velocity time graph, and then when we mention these uses, we explain them. Then in the last part, we are now going to see how we can use various expressions, the various expressions that are suitable in carrying out calculation using velocity time graph. Thank you for following us till this point. Remember, I'm still your friend and your tutor, Engineer Ike Okechukwu. Bye.